Yes,
Okay.
it starts.
So it's really my pleasure to Professor Sukanta Bose from Inter-University Center for Astronomy and Astrophysics. He did his PhD in 2001 from the University of Wisconsin, 1996, and then he joined in 2001 Washington State University, and then in 2013 he has joined IUCA, and he is the co-founder of LIGO India Scientific Collaboration, and he is also member of the executive committee of LIGO, and he has received the award from National Sound Foundation, career award. And today he is going to tell us about his one of the recent work, that is constraining the neutron star equational state from the gravitational wave. So please.
Okay, thank you, Professor Agarwal, for the kind words. So I will get started now. Is my audio okay?
Yes, I can hear very clearly.
Okay, thank you. Yeah, so this is work we recently did on finding a new family of unified neutron star equational state. And then we used it to make some projections on how gravitational wave observations that we expect in the future, combined with GW 170817 type events in advanced LIGO-like sensitivities, how such observations can constrain some of these equational state parameters. This work has been done in collaboration with Michael Forbes at Washington State University, Sanjay Reddy at University of Washington, along with his student Dave Zhao there, as well as Arunav Mukherjee in Max Planck Hanover, and Shomi De, who, when this work was begun, she was actually at IUCA, but now she is a PhD student in Syracuse. And among other people, we benefited quite a bit through interactions with my colleague KG Arun, who is a member of the LIGO Scientific Collaboration. Moving on. So the main ideas behind this work are as follows. The main plan is as follows. So we develop a family of neutron star equational state parameterized by 8 neutron and nuclear parameters. We label them as theta, that blue symbol, for the time being. We then use variations of these parameters to see what effect those variations have on the neutron star macroscopic parameters such as the mass, radius, and the tidal deformability. And notice that these parameters are, or some subsets of them, are measurable not only with gravitational wave observations, but also with electromagnetic observations such as of X-ray binary systems, which some of which harbor neutron stars. As for example, what the experiment NICER is attempting to do, which is basically to measure the mass and radius of a few of these neutron stars. So the microphysics parameters theta, for gravitational waves at least, affect the gravitational wave signal's phase, primarily the phase, by modulating the mass and radius. So as you vary these parameters, the mass and radius will vary along with lambda. So but mainly mass and lambda. Lambda itself, of course, depends on mass and radius. So let us club these two parameters, mass and lambda, as eta. But the nice thing is that in a binary system, there are 2 neutron stars. Sometimes, these may not have the same masses. So we are able to measure with some precision mass and tidal deformability of 2 of these objects in the binary system. And like we saw with GW 170817, the binary neutron star merger that was detected with multiple telescopes and LIGO and Virgo in August 2017, one can compute the joint posteriors of these parameters, right? But if there are multiple such events as we anticipate in future, and in fact, a candidate event of a neutron star merger was announced just a few days ago by LIGO and Virgo, then we can combine these posteriors across the several observations to be able to constrain first the macroscopic parameters, but then subsequently the microphysical parameters that much tighter. And so we attempt to do that in this work with simulated signals. And then to be able to estimate the measurement errors, we use the Fisher information matrix method. Ideally, we should use Bayesian methods, and currently we are, in fact, already working on that. But for the moment, we erred on the side of removing systematics that may arise if we limit ourselves to just a few neutron stars, because then the errors will heavily depend on exactly what their mass and lambda distributions are. So rather, we erred on the side of studying multiple ensembles of binary neutron star signal populations, and then averaging over the errors, the mean errors from these populations. So across the family of populations. And that way, we avoid introducing any systematics arising from exactly which 15 neutron star mergers we happen to see. And this allowed us to do some variations, for example, by examining different population synthesis models, and more about that later. But for the signal, we basically use the following. Remember, the tidal deformability parameter is best measured from the mid to late in spiral, very well with post-Newtonian theory. But then in the late in spiral, it is useful to incorporate corrections arising from numerical relativity. So keeping that in mind, our signals were produced by Dietrich et al., where for the early in spiral part, we use Taylor F2, coming from post-Newtonian theory. But for late in spiral, we use numerical relativity corrections as studied by these authors in their Physical Review D paper in 2017, as mentioned in bullet number 4 on slide 2. So I already talked about mass populations mentioned in bullet 5. So let's move on to some details. So to illustrate the type of equation of state we are studying, this is a busy slide, so I'll go through this slowly. I first show figure 1 on the left, illustrating how the pressure will vary as a function of the baryon number density as we go deeper in the star, starting from the surface, then going to greater depth. And we also show how the composition of any star will change depending on its mass. So these 3 wedges show the cross-sections of a 1 solar mass neutron star, a 1.4, and then a 2 solar mass neutron star. Their radii can be read off from this horizontal axis shown on top, going from 0 kilometers in depth, or rather in radius, to 12 kilometers. So at the surface, we use the Bain-Pettit-Sutherland BPS crust. So that's standard in literature, so I'm not going to spend too much time on that. So that is shown in blue here. Then in orange, our equation of state is modeled after the compressible liquid drop model. And I'm going to tell you a little bit about it in the coming couple of slides. Deeper in the neutron star, we have homogeneous neutron matter. This is essentially the region that is termed as outer core. And then further deep, we have the inner core, for which we use this speed of sound parametrization, something that I'm going to describe again in some more detail. So the compositions of neutron stars for 3 different masses are shown, in this case specifically for what we term as the central equation of state. And the values taken by the 18 parameters for the central equation of state are given in table 1 on the right of the slide. Again, I'm going to describe some of these parameters in more detail in the coming slides. So this is just a synopsis. But basically, for the compressible liquid drop model, you have parameters such as the surface tension parameter, but also the Coulomb screening parameter. And then we have the symmetric nuclear matter parameters as given here through the symmetry energy, the slope of the symmetry energy, the incompressibility parameters. And then we have a double polytrope to describe the homogeneous neutron parameters in the outer core. A and B are the coefficients in that double polytrope. Alpha and beta are the exponents. And then there are the proton-polaron parameters and also the inner core parameters, but more about that in some minutes. Notice that what we show on the right vertical axis in figure 1 is the tidal deformability parameter plotted in purple dot dash lines here for the two lighter neutron stars, 1 and 1.4 solar mass. Dimensionally, you can show that this should go like the energy density times the 7th power of the radius of any point in this cross section of the neutron star. So R increases as you go away from the center of the neutron star, and this calligraphic E decreases. So there is a competition between the two parameters, but if you calculate them for the central equation of state whose values are measured or given here, then you find that for these two neutron stars, the tidal deformability behaves like this, which means that the greatest influence on the tidal deformability for these neutron stars actually arises from this homogeneous neutron matter outer core. And that is going to be one of the focal points of our study. So ultimately, we'll see how good modeling of this outer core can have a bearing on our ability to measure lambda. Is there anything else I should go through? Yeah, the last thing I would like to point out is that in parentheses here, we give error bars. So for example, and we use the System International, the SI convention for it. So here 138 really means the error is basically 100%, plus minus 1.38. Here for the Coulomb screening, 1 is represents really 0.1. So it is this digit on which the error is. So the value of C here is 0.9 plus minus 0.1. And similarly for this saturation density in 0, here we want to, we are allowing an error of, here the 1 is a correction on this digit, the second decimal place. So the value of this is 0.16 plus minus 0.01 per Fermi cube, and so on and so forth. These error bars are what we call nuclear errors, which have no inputs whatsoever from astrophysics. So no inputs from NICER measurements or gravitational wave measurements. Later we will show how these errors translate to an error in this pressure versus density curve. And we will also show how astrophysical inputs, such as from gravitational wave observation, can reduce that error or make this measurement of the pressure versus density curve more precise. Any questions so far?
I think discussion will start after the talk.
Okay, fine. So next slide, slide number 3, is on some details on the compressible liquid drop model, CLDM. So this model provides a unified equation of state connecting a fixed outer crust, which is BPS for us, for density less than the neutron drip density, to the inner core, going down all the way to the inner core. equation of state. Okay, the inner core equation of state will be chosen differently, and I'll come to that in a few more slides. In the inner crust, the compressible liquid drop model, as perhaps is well known to most of the audience here, basically nuclear physicists, this constructs spherical nuclei in aspherical Wigner site cells, ensuring equilibrium with surrounding neutron and lepton gases by establishing both electric and beta equilibrium. This is similar to the approach taken in some past papers, such as by Fortin et al. And Zhnudek et al. But it differs in, so our approach differs from them in how we define the nuclear matter equation of state through this nucleon energy density. N and P subscripts represent basically the neutron and proton. NP is the neutron number density, and sorry, NN is the neutron number density, NP is the proton number density. So instead of using this nuclear energy density obtained from specific models based on effective Hamiltonians solved in the mean field approximation to reproduce empirical parameters like nuclear saturation properties, what we do here is close to a minimal phenomenological parameterization, which we'll see in a moment, that directly encodes properties that can be either measured or be calculated with some confidence. Point number 3, the advantage of our approach is that these parameters are directly connected with the unified equation of state, thereby allowing us to provide a full covariance analysis. So this is basically obtained by cross-correlating effects of nuclear parameters on the neutron star macroscopic parameters, for example. And so this tells us, for example, that changing some of the nuclear parameters couples in such a way that the effect on the neutron star observables is the same. So in such a case, we will not be able to measure those parameters individually, but maybe some combination of them. Okay, so that is also very useful. And details of that you will find in the paper that was referred to on the first slide. Finally, to establish beta equilibrium here, we include leptons model as a Fermi gas of electrons and muons at sufficiently high densities, so as the depth in the neutron star increases, using the Thomas Fermi approximation. Going to slide 5, a little more on the CLDM crust. So this, to characterize this crust, this inner crust, we introduced 2 effective parameters, essentially, to characterize the surface tension, sigma. And so this, to leading order, is determined by sigma 0, which is reasonably well measured, and its value is given a couple of slides ago, or rather, yeah, that's right, a couple of slides ago. But so this is the value you will have when you have symmetric nuclear matter, and when you are measuring things at nuclear saturation density. But as you deviate, then you develop correction terms, and which means, and we are allowing for such correction terms through this C-sim. So we therefore introduce another parameter, sigma delta, for those deviations. So CLDM for us is characterized by sigma 0, sigma delta, but also this suppression factor in Coulomb interaction that I mentioned in the table a couple of slides ago, C, which is to allow for the diffusivity of the proton charge distribution. But to recap, so the CLDM parameters, deviating from sigma 0 are characterized by sigma delta, which is about 1.38 megaelectron volts per Fermi square, and this Coulomb suppression factor of 0.9. Yeah, so by the way, again, these central values shown are for what we term as the central equation of state. We will look at deviations from this equation of state as well. Now, I'm going to jump to the inner core before I come back to the important discussion of the outer core. So the inner core, for that we do a speed of sound characterization as follows. So above densities twice the nuclear saturation density, which we expect to be quite prevalent in the core. The equation of state is, as known to this audience, is unconstrained. So the typical approximation that people use at high densities is to characterize it with a polytrope. But here we choose what we believe is more physically sound, high density equation of state parameterized in terms of the square of the speed of sound. So here, big C as a function of the baryon energy density is written as this ratio, where Cs is the speed of sound as a function of E, and C itself is the speed of light. And this, of course, as is known, is related to the derivative of the pressure there with respect to E. And for causality, of course, we require this to be less than or at most equal to unity. But we know from perturbative quantum chromodynamics that this value is expected to reach 1/3 at asymptotic densities. So that is described in this picture here, where at large densities, so basically coming close to the center of the star, we expect this parameter C to reach a value of 1/3. But early on, it has a value that can be matched with known parameterizations at low densities. So, but then we also know that at intermediate densities, it reaches a maximum and has a quadratic behavior as a function of E. But exactly how large or small this convexity is a degree of freedom at the moment, which is not constrainable by any other way, but perhaps by observations. So we allow for that degree of freedom and see if this can be constrained observationally. So to recap this figure, although the form of the function C, the big C, is unknown at finite density, its qualitative form at finite temperature suggests that it may first peak before returning to the asymptotic value of 1/3. Second, we therefore include a simple parameterization for C as a quadratic polynomial in E, as shown in this figure, smoothly connecting to the homogeneous equation of state at fixed transition energy density EC at some low density, then reaching a maximum, and that again is a variable parameter C max for us, but we know that it cannot exceed 1 because the speed of sound cannot exceed the speed of light. And that happens at, again, yet another variable parameter E max in this figure at that point. So C max, E max are variable parameters, and so is this transition energy density EC. So therefore, the core equation of state is, it is characterized by this curve and these parameters, EC, E max, C max, which for our central equation of state have these values, 350 megaelectron volts, 0.8 gigaelectron volts, and 0.8 respectively. And these error bars here are for what we call the nuclear equation of state. But we will, of course, vary these parameters to check how well those new equations of state with different values for these parameters will be constrainable with observations or not. Okay, now we come to the outer core where I'm going to spend some more time. So here, before we introduce the double polytrope that is used to characterize this homogeneous neutron matter with some proton fraction, non-negligible, which changes with density, what we do, our rationale is explained as follows. Number one of the main features of our analysis is to parameterize the nuclear matter equation of state as an expansion in the proton fraction. Okay, XP, which is given as this number density of protons divided by the baryon number density here. So we expand the equation of state in terms in powers of the proton fraction about pure neutron matter. Okay, going towards symmetric, I should say, nuclear matter. This is in contrast to the common approach of expanding about symmetric nuclear matter in powers of the isospin asymmetry, which is basically this ratio between the difference of those two nucleonic number densities divided by the sum of those densities. The common approach, of course, has proven very useful because it allows one to directly connect experimentally relevant properties of symmetric nuclear matter to properties of neutron matter. This connection, however, is predicated or based on the so-called parabolic approximation, where we expand the nuclear matter in orders of the isospin asymmetry parameter beta p only up to quadratic term. And this is valid if the quadratic term is expected to dominate over quartic and higher orders, which of course is understandable. Now, there is some support for this assumption below saturation density from relativistic DBHF calculations, as for example, it's shown in Lee et al. From this 1998 paper, but also in this paper by Gonzalez, Bocura, and so on, such as by Lee et al. The problem, however, is that the validity of this parabolic approximation is not established at densities at or higher than nuclear saturation densities. But as you saw in figure 1 a few slides ago, depending on the mass of the neutron star, the outer core may already harbor densities at around the nuclear saturation density. So that is why we chose to do a different parameterization of the matter there. So any form of neutron-matter equation of state can be accommodated with quartic terms without spoiling global mass fits, as was shown recently by Aurel Bulgark and his collaborators in this PRC paper. And for this reason, we start with the parameterization of pure neutron matter and then use the properties of symmetric nuclear matter to constrain extrapolation in the proton fraction. So this will be the rationale we adopt in this next slide, slide number 8. So, so as I said, we do not expand the energy per nucleon around symmetric nuclear matter, but rather around neutron matter in orders of xp, the proton fraction. So which is why this nucleonic density, energy density, is to leading order this neutron matter density, and then to subleading order have corrections in the proton fraction related terms, which of course includes also the proton rest mass and the polaron related corrections, the details of which are given in our paper, but also higher order corrections in the proton fraction. Here, m star is the proton's effective mass. This coefficient is again well known. It involves, for example, corrections including Planck's constant. But there are also terms which are not well studied, such as F2 and F3 as functions of the baryon density. And these are terms that we constrain by matching against symmetric nuclear matter equation of state. So this is what I meant from that last bullet on the previous slide. But for neutron matter itself, underlined in this magenta color, we adopt this double polytrope shown in the blue box here. You can ignore this intermediate term. Basically, yeah, E is the energy and energy density, but you divide it with this neutron number density to get the energy as a in terms of the neutron number densities. So to leading order, you have the corrections from the neutron mass, but then you add these double polytropes. A, B, alpha, beta are the coefficients and the exponents whose values we gave for the central equation of state on the third slide in this talk. The corresponding pressure, which is obtained by taking the, is gotten from here by taking appropriate derivative, of course, is therefore also characterized by A alpha B beta in this following form. I'm going to show you the values of these coefficients in a minute, but basically the red terms characterize the outer crust, even close to the material close to the inside of the inner. I'm sorry, let me backtrack. The red terms characterize less dense matter in the outer core, and this matter goes all the way to almost the inner crust, and the blue characterizes material that is more dense, which comes very close to the transition to the inner core. This form has been found to accurately fit quantum Monte Carlo calculations of the equation of state using nuclear Hamiltonians with realistic 2 3-body forces. It is also consistent with quantum Monte Carlo results based on chiral effective theory interactions. Again, the references to these results are given in our paper. If you're interested, I can point you to them. And as I already mentioned, these higher order expansion coefficients in nuclear in proton traction are obtained by matching against the symmetric nuclear matter expanded to quadratic order in the isospin parameter beta p, and also quadratic order in the expansion away from nuclear saturation density. So to recap, once again, these are our central equation of state parameters, and we vary about these parameters to obtain different equations of state. So diagrammatically, these are the different TOV stars you will obtain. For example, if you use values for those 18 parameters that correspond to what I have been terming as the central equation of state, so that gives you this kind of family of TOV stars. But then if you vary about these parameters to make them softer or stiffer, you get different TOV MR curves. So for example, so for the double polytrope parameters A alpha B beta, but also the transition density to the inner core, and also the maximum value of the speed of sound in the inner core 0.8. Okay, these are the values chosen for the central equation of state. And once again, in case you missed it, one last time, A alpha B beta are these terms that characterize neutron matter using this double polytrope expansion. Okay, so these are the values for the central equation of state. For what we term as the soft equation of state, which is the most compact object for any given mass. Okay, so this MR curve. The soft equation of state has smaller values for all of these parameters, A alpha, B beta, compared to the central values. Here we don't play with the EC, Cmax parameters. We change them for other equations of state, such as low EC, high EC, depending on the density at which the transition to inner core happens. Similarly, we also play with the maximum value the speed of sound can take in the inner core. And so we have another equation of state which has the same parameters, except the Cmax is lower at 0.6 as opposed to 0.8. And then there is also a co-transition parameter variation that we study, which we call E-trans. So all of these various parameter families give rise to different MR curves and therefore different equations of state. Stiffer has larger values for these densities and these double polytrope coefficients compared to the central values. So 0.7 as opposed to 0.5 or 2.5 versus 2.3. On the other hand, soft stiff has smaller values for the low density part of the equation of state and higher values for the high density part of the equation of state. Stiff soft is just the opposite. So stiff soft is basically this curve here, somewhat between the soft equation state. Maybe, alternatively, we could have called this soft, because it is softer here as well as there, low and high density parts of the double polytrope. This is stiff soft, this is central, this is soft stiff, and then this is stiff or just stiff. Okay, and the rest are depending on how we play with the parameters of the inner core. So this sets out the different equations of state that we then attempt to constrain in our simulations of binary neutron star signals and nicer constraints. But we introduce one other playing field here, which is basically how the neutron star masses are distributed in the LIGO observation volume. So there we tap into this well-known work of Dominic et al. From 2012. They actually analyzed various models. We limit ourselves to just 4. Otherwise, these plots will be very cluttered and confusing. So the 4 models we chose are as follows. We vary the solar metallicity. So we have one model where the metallicity is exactly the same as our sun's, and the second model is subsolar, meaning it has 10% less compared to solar metallicity. So these less solar metallic stars are usually heavier in mass, so correspondingly their remnants will be different in mass compared to those formed from large stars with the same metallicity as our suns. So that can give rise to a different neutron star mass distribution. But another factor that we vary, adopting from Dominic et al., is how much mass is transferred in what is known as the common envelope stage, where one of the star grows to a red giant phase, thereby enveloping its compact companion, and so there can be some mass transfer, thereby redistributing the masses of what eventually will be a double neutron star system. And depending on differences in details of the stage, there are 2 different models, Model A, Model B. One of these models allows for more asymmetric masses, meaning the secondary mass can be relatively less compared to the primary mass M1. In the other one, the 2 masses are more similar. So when we limit ourselves to the nuclear equation of state, meaning it has the central equation of state values, and the errors are as noted in the parenthesis shown here. Okay, typically, some of them as high as 100%, but there are some that are as low as about 10%. If you do that, then if you create, so what we do is we start with TOV stars drawn from these various populations. Okay, so this is subsolar metallicity Model A, solar metallicity Model A in orange. Okay, black was subsolar Model A, and then green subsolar metallicity, but Model B for mass transfer, and then solar metallicity in red with submodel B. Okay, but we also have a uniform mass distribution where M1 and M2 have uniform values between 1 to 2 solar mass. Okay, and then we see for these different populations, essentially meaning and remember, for those different populations, we'll be sampling different parts of this MR curve. For uniform population, we'll be sampling very disparate neutron stars because they will go all the way from close to 1 to 2 solar mass. But for some of the other Dominic et al. Population synthesis models, we may sample only a relatively small region of this M versus R plane. So our quest here is to see how the mass distribution affects the errors. Okay, assuming they're all just coming from the mass distribution. Okay, so when we do that, we find that the uniform mass distribution population has the largest errors. The other ones have relatively small errors. Okay, and not much difference between them if you allow for these error bars, where these error bars come as follows. Remember, I said, oh, these are, okay. For these errors, we assume that for every experiment, we have 15 binary neutron star mergers in advanced LIGO design sensitivity. Now, depending on which 15 neutron star mergers you choose, randomly drawn from these populations, you will get a spread in this error. And so this green, faint green spread is the error arising from exactly which 15 neutron star mergers you choose with what kind of masses. Okay, and the mean is shown in black here, subsolar A. So there is some spread there, and that spread pretty much covers almost solar B as well. So there is a little difference depending on how these mass models are distributed, but uniform actually is least constraint. Regardless, all of these errors are well below 20% in pressure as a function of nuclear number density at a density of twice the nuclear saturation density, okay, where N0 is the nuclear saturation density. So this bodes well, because currently with GW170-817, if you try to see what kind of errors we have in the pressure density curve, it is in the ballpark of almost 100%. But then that's not a fair comparison, because GW170-817 was not observed in A-LIGO design. Rather, in August 2017, the sensitivity was at least about a factor of between 2 and 3 less than the advanced LIGO design. So future detector upgrades will make things more sensitive. Number one. Number two, here we include posteriors from 15 observations as opposed to just one object. But of course, distributed between 100 to 400 megaparsec. So this makes it less rosy a picture, because 170 and 17 was at a distance of 40 megaparsec, albeit in a less sensitive detector. So, but just remember those caveats. By the way, if you're wondering what this is if there are no gravitational wave observational inputs which were folded in here, but only the nuclear errors that are shown in parentheses in table 1. So this is showing that astrophysical inputs for that nuclear central equational state actually do improve I think this should really be central equational state. So the central equational state with astrophysical inputs improves over just this nuclear equational state. Okay, so let me recap. So this curve is the nuclear, what we call the nuclear equational state errors, shown in parentheses in previous slides, whereas these curves are pressure versus number density errors obtained after incorporating gravitational wave observations, albeit simulated from 15 sources at a time. And so observations here obviously are helping in reducing those default nuclear errors. In this picture, we see the effect of varying the inner core parameters. Okay, so once again, this blue dash curve is the nuclear errors. The remainder errors are when astrophysical observations, basically again, 15 binary neutron stars simulated, taken into account. But what we are varying is all other parameters are the central equational state parameters except the core parameters. So this black is the central equational state parameter with 15 gravitational wave observation, and the orange and green and so on and so forth are when you vary the inner core equational state parameters, such as the where the transition is happening, whether it is happening at low energy density or high energy density, and if you're using a lower value of Cmax, like 0.6 as opposed to 0.8. So you notice that there is some sensitivity, and I would say thankfully, to what the inner core parameters are. For some cases, and there's a reason for that, and the reason is that some of these changes have very little effect. For example, when you're looking at low transition to inner core happening at a low energy density, right? When that happens, then basically the degree of homogeneous neutron matter, which I showed in green in the outer core, becomes very limited. And remember, that is where we have greatest influence on the tidal deformability parameter. That influence goes away. So, and that is why these errors are large. In other cases, that influence is greater. And so we are able to measure lambda more accurately, and therefore the pressure density curve is also measured more accurately. In this slide, what I do is I again limit myself to the central equation of state in black, but now I add the following possibilities: that there is a GW170817 like event at 40 megaparsec, plus 15 other LIGO events between 100 to 400 megaparsec, right, in a LIGO sensitivity. When that happens, then you notice that at twice the nuclear saturation density, you will be able to constrain the pressure with an accuracy of something like 13–14%. On the other hand, if you had just this once again, as for reference, is always the default nuclear errors from the table 1. If you had just one nicer event, as the mass radius measurement from this pulsar system with 5% precision in mass measurement and 10% in radius. If you do that, then the pressure measurement actually improves relative to the nuclear default parameters to close to 30%. But if you actually involve a single GW70817 event at 40 megaparsec, the error already reduces below 20%. Okay, so this is 20% at twice the nuclear saturation density. But additional observation, like one more LIGO or 15 more, 100 more, they will of course reduce the error more and more. So in conclusion, in this work, we developed a family of neutron star equations of state, parameterized by 18 neutron and nuclear parameters. For the outer core, we expanded the EoS around neutron matter instead of symmetric matter. So that was the most important point of departure relative to many of the past analysis. We reported for the central equation of state that one can measure the pressure versus density curve better than 20% accuracy at twice the nuclear saturation density in plausible gravitational wave observation scenarios. By foreseeable future, I mean a future expected in the coming few years. And this paper discusses additional equations of state, not just central, but there are too many curves. If you are interested, they're all given in the last few pages of the paper on which this talk is based. And of course, as you change those equations of state from stiffer to softer, the measurement errors also change. But in many cases, they still remain within 20%. So which bodes well. We also present the effects of various population models on errors. But the weakness of this study is that we use Fisher methods. But we are now working on analyzing 170817 data with Bayesian methods and repeating the simulation analysis here also with Bayesian methods, which of course are more computation expensive, so they may take a little time. Thank you very much for your attention. Yeah, if there are any questions, I can try to answer them, or maybe some of my co-authors may be on the call too, and they may also pitch in.
Yes.
Hello.
Yes, please.
Hello, sir.
Yes, I can hear you. Please go ahead.
It was a nice talk, sir. So one of your slide, you have shown that the stiffer and the soft equation of state, where you have shown so many stiff and the soft equation. Sorry. Hello. Hello.
I can hear you.
Hello.
Please continue.
Sir, one of your slide, you have shown that there are so many steep and soft equation of state here. So here one thing I can notice that when you change the equation of state from soft to steep or vice versa, the radius changes too much, but not the maximum mass.
Oh, good question. So we did keep these ranges in a ballpark where the maximum. So there is some change in maximum mass, but it's all limited to between
But
about mass and 2.5. That is by design.
So why it is so? Only if you see the variation in the radius is too much, but the variation in the maximum mass is not so high.
I'm hazarding a guess that we can come up with parameter distributions where the mass can actually rise as well. It's just that we always restricted ourselves to have maximum mass in this range.
Okay. So you have restricted your maximum mass, but
yeah. I can check back and get back to you, but I think it is not impossible to have equation of state parameter values here, given we have 18 parameters, so that you can actually have an equation of state that is still within about 11 and 12 kilometers, but has a higher mass than what you see here.
Okay. So another question is that, so how you decide the transition density from one region to another region, like suppose inner core to outer crust? So how to decide that transition density?
Do you want me to take this, Sukanta?
Yeah. So Professor Michael Forbes is here from Washington State University. I'll let him answer this question.
Hi, everyone. Sorry, I apologize. My voice is, I've got some sort of laryngitis, but I hope you can hear me.
Okay.
So basically, once you specify the form of the homogeneous equation of state, then the transitions to the outer crust are defined by just equilibrium with the compressible liquid drop model. So there's nothing really fixed there. It just comes from matching the with the compressible liquid.
So that density, how you get that density? At which density that two phases will be mapped?
So it's essentially where nuclei will start. There's a point where nuclei will start dripping out of the nucleus, and that's where the compressible liquid drop model starts. And then at some point, the energy of the homogeneous molecular matter will be smaller, or the pressure will be greater rather, than that of nuclei with neutrons that have dripped out.
Okay. So,
no, we don't do anything fancy here. I mean, of course, it's known that there will be pasta phases of some sort, or maybe even glassy phases, and we just use a spherical liquid drop model here. But for the purposes of the overall equation of state, they have very small effect. Of course, they're very relevant for glitching and things.
I think in the outer core part, there must be some nuclei in the cluster form.
Yes.
Outer crust.
So the far outer crust is this Bain-Pethick-Smith tabulation, and so we use that for the extremely outer for the outer crust.
In your equation of state, have you considered that in the outer crust they have formed a nucleus?
Sorry, they have what?
In the outer crust part, maybe the density is so less, so they can form the nucleus. They will not.
Correct. So in the outer crust, we use the tabulated values from Bain-Pethick and Smith. So in principle, the liquid drop model should sort of give you some idea of that, but it misses shell corrections, etc. And so we use the tabulated data for the extreme outer crust.
Okay.
And then the CLDM, compressible liquid drop, once the nuclei start dripping out.
Okay, so that the outer crust has no, actually, this figure shows that they have no any sizable effect on the tidal deformability.
Correct. The outer crust is very, very small, so it's in the region you can barely see. You can't even see it on the plot. It's this blue region and the stars up above, but then that's compressed to an extremely small physical space.
So most of the contribution comes from this outer core, homogeneous
part. From the outer core and a little bit of the inner crust.
Inner core. Okay. Thanks.
With the exception, of course, of the stiff equations of state. So this equation of state was sort of our central values. If it gets much stiffer, then you have much more core. And so you learn less about the homogeneous part and more about the cores.
Okay.
And one question, just back to your previous question about the maximum mass. I mean, it's hard to make neutron stars that have a much larger maximum mass because without violating the speed of sound constraint, the speed of sound has to be less than the speed of light.
Oh, okay, okay.
So with these values that sort of work fairly well for Monte Carlo, I mean, there's not a whole lot we can do to make it really large. Right.
Okay. You have maintained the speed of limit that it should not be maximum 1. So that's why the maximum mass is not differ too much.
Yes, exactly, because causality puts that. Sukanta, can you go back to the equation of state, this core speed of sound? What?
Hello.
So in this, there's one different equation of state we used in the core, which is this purple line, which we call the core transition. And here we allow for the possibility of a first order phase transition yes, that one. Followed by a constant speed of sound that basically is large enough to support a 2 solar mass star.
Okay.
So if you were to bump that up to 1 to make it sort of maximum stiff, then you could increase that core, or the maximum mass a little bit. But it's a little tricky. There's not a whole. It's hard to make very, very strong equations of state with our parameters. Sorry, very massive stars.
Okay. Thank you.
Okay. Hello.
Yeah, please go ahead.
Okay, this is Bhuya. So my question is a continuation of that question. That means how you distinguish the inner core and the outer crust divided into two parts. Means inner crust and outer crust. According to the density, or you have some parameter to distinguish the two part of the crust.
So this distinction that we have here is based on whether or not you have homogeneous nuclear matter, that's the outer core, or whether you have nuclei with an embedded neutron gas, that's listed as CLDM, that would be the inner crust, versus just pure nuclei, which would be the outer crust.
Okay.
So those densities come out based on our parameters. If you change the parameters, the transitions change.
Okay. This is based on the density of the parameter is based on the density or any other factor.
So the densities at which these transitions occur depend on the parameters. But the nature, our labeling of the inner versus outer crust, etc., those happen when the nature of the nuclear matter changes from homogeneous to a crystal to nuclei without neutrons.
Okay, one more questions. Like recently, there are some paper coming that the crust the tidal differential is very sensitive to the crust of the neutron star. So in your case, also inner crust playing very great role on the tidal deformability, and the outer crust have not much role on that. So can you give some quantitative value that how much the sensitiveness is there in the inner crust and outer?
I mean, the best we can sort of do, I mean, you can look at it on a case-by-case basis, but these purple curves give you sort of the heuristic, showing you where the contribution is coming from. And so for our central values of the parameters, we are mostly dominated by the homogeneous matter and the inner crust, and there's very little contribution from the outer crust.
Right. I mean, if we have observations of low mass stars,
yes,
they're all maybe 1 or 0.9 type stars, then we can have some hope of this crustal part influencing the tidal deformability. But we still believe that it will have a relatively smaller influence compared to other parts of the star.
Okay, thank you very much.
Once you get to lower masses, though, if you remember the mass radius curves, the radius can balloon and get extremely large.
Okay.
So if you start hitting those stars, then you'll be sensitive now, because the outer crust will be at very large radius, so that that factor will increase.
Okay. Okay. Thank you.
Welcome. Any other questions?
Yes, I have some questions. I am Chiranjeev speaking.
Please go ahead.
Yes. I mean, following one of the previous questions of not getting very high mass, but you are being able to get a lot of big range in the radius of the star. My question is that if this nicer observation, they will come up with a very specific value of the maximum mass and the radius simultaneously for a single star. How do you think that will have effect on your model?
Yeah, so in the case of the nicer object, we already know, like the mass is, I think, about 1.4, but we are aiming to measure it with an accuracy of something like 5%. The radius is less well known, but nicer may find it to about 10%, right? So when you do that, you're already constraining this part of the MR space, right? So which in turn will also translate into a smaller region in the pressure versus density diagram.
Okay.
So that is how we translate the nicer measurements to the pressure versus density, going via the mass radius plane, because we know exactly how our parameterizations are limiting these curves in this plane.
So, because what I see here essentially going from soft to very stiff, the mass radius plane changes altogether. I mean, if you have a very specific value of mass radius, then at least in that mass radius plane, you have a very specific region where your equation of state has to go through.
Yeah. So let me give you an example. So suppose nicer measures the mass to be 1.4 plus minus that 5%. So that will just be a very thin line here, okay, or not very thin, but somewhat thin slab here, okay.
Yes.
But if radius is measured, say at 11.5 kilometers, plus minus again 10%. So that will then tell you cannot change these values, let's say about our central value, by more than what is already sandwiched between, roughly speaking, the stiff soft and soft stiff equations of state. So in other words, nicer measurements are translating into ranges of our parameters, and these ranges of parameters in turn will constrain the pressure versus density curve, such as the one given here, right?
Okay.
So and we find that yes, for nicer, we are able to do better than what the default parameters are. So this is nicer, but the default parameters, of course, with somewhat larger errors was this. So nicer does improve upon it, but essentially it is coming from the MR plane via the microphysical parameter constraints. Whereas with LIGO observations, we are also able to tap into the lambda constraints, the tidal deformability constraints, which add to what nicer alone is able to do.
All right.
At least for this pressure versus density diagram, given that our parameterization is specifically designed to be able to put constraints in this diagram.
Okay. Regarding the density you choose for different phases of the star, I have a different question. How do you discriminate the inner part of the outer core and the outer part of the inner core? I mean, sorry, no. Let me rephrase the question. How do you differentiate the less dense outer core and high dense outer core? You use this different polytrope of quadratic and then quadruple expansion in your energy density for the outer core. How do you?
Yeah, that's a good question, because I already mentioned that. I mean, for part of it, you'll have basically almost just neutron matter, but then gradually it will transition into a nuclear matter with a greater fraction of protons. Michael, do you want to address that?
Well, yeah. So once you fix all the parameters for the polytrope and for the polaron and matching symmetric nuclear matter, then the equation of state is just what it is, and we solve for beta equilibrium as you go from the outer part of the outer core to the inner part of the outer core. And so the proton fraction just changes, the density increases, and you end up with whatever pressure you end up with.
What I asked is that, can you go to the next slide? I think I can address the question more specifically.
Okay.
The next slide. No. Where you have this red line and blue line. Yes, here. You see here, you for the red term is for less dense outer core.
Correct.
That means which is closer to the inner crust.
Correct.
And the more dense, which is closer to the inner core.
Correct.
So
that
here
separation only comes because of the power, because beta is much larger than alpha. So it's kind of a funny parameterization. These two terms are not linearly independent, but this double polytrope has been found to fit the quantum Monte Carlo data pretty well. And it has both terms throughout the entire homogeneous region. It's just because the beta is larger than alpha, the second term dominates in the dense at high densities, and the first term dominates at low densities.
Yeah, because the way it is discriminated, the outer part of the, I mean the dense part of the outer core and the less dense part of the outer core, I was almost thinking as of a transition like the core and the crust, but it is not the case.
It's just this particular form of the polytrope. This is smooth. Nothing changes within that outer core.
Okay.
Yeah, it just the which term dominates is the first or the second is because of alpha and beta. Beta is larger than alpha.
So can you go to the other slide where you have this relative error on the neutral pressure for 2-3 different figures? I think you have. Yes, this one or the next one. You here emphasize more on your central equation of state, but you have an option. For example, here you have this high EC curve, which gives you even lesser error.
Right.
So does it mean that the more LIGO data you put in your theory, the better error curve you'll get from your theory?
Yes. So there's right. Probably look at the next slide. So here you see that if you go from 15 observations to 100 observations, all at greater than 100 megaparsecs, then you do get some increase, but it's not so much.
Yeah.
And how much it affects in the mass radius curve?
No. So this is one of the major effects here is that the error changes like square root of the number of sources. And not linearly. So that is why,
of course.
Yeah.
I mean, it does not mean that the more number you have, like
Correct.
more change you have, but
Correct.
with more number, your change is more likely to go down also. But what I'm asking is that when you have this red line here and the black line, the central equation of state, how they stand in the mass radius curve?
Oh, so remember these are errors. So
we don't have that precisely, but
Right.
one thing you can do, the black solid line is the central equation of state, and then the outermost variations here are basically at the limits of nuclear errors. Right, so we change the parameters all within that to the full extent of the errors that we list in our table. Right, so A, B, alpha, beta, those are the most central dominant parameters, and so we increase them by the full sort of. So in some sense, you can think of those as fairly extreme variations within these equations of state. And then if you go back to the, sorry, it's a little convoluted, but if you go back to the other plot, then you can see what that change in mass radius, that corresponds to the errors in the top curve, the nuclear curve.
Yeah, but so I see your point. I mean, basically, yes, we can attempt to translate the errors to the MR plane and say, but that's difficult. The reason is the following. I guess that's one of the questions you're implying, if I'm not mistaken, that how will the red curve look here, or what will be the impact of the
yes, exactly. That is my question. Yes.
Right. The impact of the red curve, one might imagine, but not quite correctly, is that it will make this black curve fuzzy, right? Because the red curve really means that there is an error about this. I mean, we know that nature has, hypothetically, that the nature has produced a population with this central equation of state, But with live observations, we are able to measure this only with error bar. So we rather will have some error region here and not this curve. But that's, so you may pursue that route, but I think that way you will not be able to get the most out of your observations, because if you want to spread things out in this MR plane, what's happening is that 15 binary neutron stars is actually quite a lot, because there are 30 objects there, right? 30 neutron stars.
Yes, I agree. I completely agree with you. Yes.
And there are, so each of them is some point here. Okay, maybe some points are more clustered compared to other points.
Yes.
Then individually, if you want to make this fuzzy, that is like saying individually you want to measure one of them. If you try to individually measure the mass and radius of each one of them, then they will be large ellipsoids. Okay. And so you will have lots of 30 large ellipsoids merging. A more powerful technique is to say, okay, if you combine those posteriors into a single or a smaller posterior for a smaller number of parameters, because we are not trying to fit 30 objects here. You're really trying to fit around a smaller set of parameters, such as these ones here. Okay, then that's a lower dimensional problem where the posterior narrows down quite a bit to be able to give you the green curve, the red curve in that pressure versus density plane.
All right.
If you want to get some estimate, though, so the nuclear errors at 1.5 times saturation density are about 50% in the neutron pressure, and then that red curve brought it down to about 10%. So the largest, from here. So on the mass radius plot, you would expect going from the distribution that you see, which corresponds to these 50% errors, reduced to about 10%. And so you can sort of imagine what of course it's nonlinear, but you can sort of imagine what that would do to the mass radius curve, reducing that by a factor of 5 in width.
Yeah. Okay.
Does that make sense?
Just last question.
Okay.
Now regarding the crust, now the current calculations say that the crust can give you a reasonable doubt in the radius range of the star. But here in your theory, do you have this scope to incorporate if the radius is changing because of the crust?
So what effect are you talking about specifically?
No, specifically what I'm saying is that, because of the uncertainty in for example, the transition density from core to the crust, and also the central density of the star, depending on what mass you have, the radius of the star can depend on largely on the size of the crust. Depending on the star, your crust can change by almost by say 600 meters.
Sure.
So
that's basically what you're seeing here. In the 2 solar mass star, the outer crust is very, very small, very thin, and in the 1 solar mass star, it's very large.
Yes.
So that just comes out from the physics, assuming that the tabulated nuclear equation state data for the outer crust is correct.
That effect of change in the crust is only embedded in your CLDM parameters, nothing else.
Yeah. So in principle, you can take our full equation of state parameterization and maybe build a population of several low mass stars and see how accurately you can measure. Yeah, but then it will be really trying to measure CLDM parameter than anything else. And while you may do that, our physics inputs really were more in this region than there. This physics is already known. We borrowed it from somebody else. Is that fair to say, Michael?
Well, this is still a model. You really want to solve this properly using some self-consistent approach. And as I say, there are pasta phases and different transitions there. Dake, are you there? Because Dake did a little bit of an exploration of phase transitions in this region to see how much it affected the equation of state and the results. But I don't think it had a very large effect.
Right. The effect is tiny, right?
So if you change the compressible liquid drop model, or you change how you match and things, then you might have some small phase transitions that could change the structure of the crust, but it doesn't really affect the lambda and the constraints that we were able to get from these stars. Again, if you consider much lower mass stars, then that picture could totally change.
Yeah, and just another very, this might be a very foolish question. I mean, usually the kind of equation of states I have used so far, I do not discriminate the inner core and the outer core. I mean, my I mean, beta equilibrated matter goes all the way up to the core. I mean, the center of the nucleus.
Okay.
So those parameters what you have used inside the inner core. First of all, how do you kind of probe them? I mean, in a way, because you can parameterize them in whatever way you want, but to probe them, what is the way? And if you just use the uniform matter till the center of the star, will your result change by a drastic amount?
So if you go to the slide with the core equation of state parameters and the constraints, keep going. So the one with the constraints. So the answer to your second question, the green line at the very bottom corresponds to a high transition point. And so that corresponds to deferring the transition to this speed of sound core parameterization to a much higher density, above 3 times.
All right.
Right. And so then, of course, you get better constraints on the nuclear matter because the whole star is made of that. So that's the second one. Yeah, the green region will now extend much deeper to 3, which in this case is almost all of the star.
All right. Okay.
But we don't know where the nuclear equation of state breaks down, and so
yes. That's why I asked the question. Yeah.
And
there's no way to probe your inner core parameters what you have used here. That's why I asked the question.
Right. I mean, there's possibilities of phase transitions. There's possibilities of changes in the inner core parameterization that could allow for multiple branches of stable neutron stars and things like that. So there's really a lot more that one could do to probe that. We've chosen a fairly reasonable range of parameters, but we haven't fully explored what could happen in the core. And you see from that other plot that if the core, for example, has a very large first order phase transition, then the equation of state might be very stiff and then everything collapses. And so you don't learn much about nuclear matter at all, right? This low EC parameter. However, you will see that once you get data, you'll find out if you have a really stiff equation of state, then you have to sort of look at whether or not that's coming from the core or that's coming from the a stiff nuclear matter. And so you do get information about both of those depending on what types of stars you measure.
Right.
But yeah, our knowledge of what's happening in the core is very, very poor, and this is just a guess that has all reasonable physics that we know put in, but it could be very different.
Okay, thank you, Professor Bose. It was a very, very nice talk. Thank you.
Thank you for the questions.
Professor Sukanta, I want to ask one thing.
Yes.
Hello.
Please go ahead.
Whatever equation state you are using in the outer core region, how it is consistent with the properties of the finite nuclei?
So the parameters that we fit here are coming from quantum Monte Carlo calculations with a variety of both chirally motivated equations of state and various different three-body interactions. And so, of course, there's a very large program to try and figure out what happens with small and medium mass nuclei to make sure they're consistent with the chiral interactions. And so part of that goes into the values of these parameters. This equation of state here is consistent with interactions that do reproduce nuclei fairly well. Does that answer your question to some extent?
Yeah, actually, I mean, recently we did a calculation and we found out that most of the parameter at the saturation density, like energy per nucleon or effective mass or the symmetry energy or the slope, many of these parameters are very well constrained from the properties of finite nuclei like binding energy, charge radii, and these various multiple resonances. So basically, there is very small room to, I mean, vary the nuclear matter parameter in the outer core region actually. And since the outer core region is connected with your inner core and the crust, so in a way, it controls
so this is a very important point. what we've done here is that we have expanded from neutron matter and then used the properties of symmetric nuclear matter to constrain that expansion. That's the F2, F3, F4, F5 terms in equation 1. So we've taken the approach of using the quantum Monte Carlo data, assuming that we can improve that, figure out three-body forces, and get the form of the neutron matter equation of state, and then construct a full homogeneous equation of state, extrapolating from neutron matter and fixing it by nuclear matter properties. And what we find when we do that is that the saturation and symmetry properties actually play very little role in the neutron star overall equation of state.
Actually, our research paper basically, is telling us something different. We found that by the time we really constrain the properties of finite nuclei, given a function like a scum functional, we do not have much freedom to vary the high density behavior of the equation of state.
So to what order did you go in isospin expansion? That is true if you only consider this parabolic approximation, where you expand and assume that the quartic and higher order terms in beta.
No. We did not use any parabolic approximation. We really used the exact scum functional. So basically, it was not really the expansion around any. We didn't really.
But the Skirm functionals have a built-in. You can add to Skirm functionals higher powers in beta. This is essentially what we did in the work that Sukanta mentioned with Oral Bulgak, is that we built a new energy density functional that is Skirm-like, but minimal. And we find that when you add the beta to the fourth terms, you can allow basically any neutron matter equation of state that you like, and you can still fit all the nuclei globally, all their properties, the charge radii, binding energies, separation energies, etc. And so adding those beta to the fourth terms gives you enough degrees of freedom that you can essentially separate the neutron matter equation of state from the properties of symmetric nuclear matter. We were
I am not talking about the decomposition of the equation of state in terms of the symmetric or the. See, what we do is we really take the scum functional where we do not decompose our, asymmetric.
Right. So what we're saying in this paper, we have a functional here which is better than Skirm functionals. So Skirm functionals have something like 20 or so parameters up to. We have a functional with 4 to 8 parameters that can fit all the masses and does a better job than most of the Skirm functionals, unless you do corrections beyond, not self-consistent corrections. So you take a look at this functional, but within this functional, we can fit all the masses as you would with a Skirm functional. Okay. And then you can add these extra quartic terms and they don't affect the mass fits.
Okay.
That's sort of what it's saying here. This is a very important point and somewhat controversial, because there are these calculations with perturbative techniques, etc., that say what you learn in nuclei should tell you something about the neutron matter equation of state, but we don't see any reason that should hold, at least at higher densities. And we find that when we allow these beta to the fourth terms to be included, we can allow for almost any neutron matter equation of state, and so they kind of decouple. And it's not decoupling because it's artificial, it's decoupling because there are functionals, Skirm-like functionals, that can fit all the nuclear properties to a high precision and still allow for variability in the neutron matter equation of state. Does that make sense?
Yes. Thank you.
Yeah, so I think this feedback was very useful. So maybe it's like on the last point, perhaps we can add some explanation in our paper to help address such a question.
Yes.
Okay. So Phil, do you have any comment?
Is Phil there?
Yes, sir.
Oh, I should also acknowledge Phil now. We do that in the paper because he carefully read the whole paper and shared some useful comments with us. Thanks, Phil.
Okay. I think we don't have any other questions. Let us thank Prof. Sukanta.
Yeah, thank you, Sukanta, very much.
Thank you, sir.
Thanks also to my collaborators. Good talking to you again.
Yes, thank you.
Yes,
Thanks.
thank you. Nice talk.